Alright, Grizzlies, we're on Chapter 6, Exponential and Logarithmic Functions. 6.1, Exponential Growth and Decay Functions. Exponential growth is in the form of y equals a times b to the x power. For our parent function, our most basic function, we have f of x equals b to the x power. And for growth, b is greater than 1. Alright, we have this base, which is b, and the general shape is always going to look something like this. Okay, it's going to go kind of slowly, and then it's going to shoot up really fast with this exponential growth. Your x-axis is an asymptote, which again means it's not going to touch that line, right? It's going to approach and get more and more closely, but it will not touch. Okay, it is also going to hit points 0, 1, and 1b. Okay, it's going to hit, and then it's going to exponentially shoot up. Okay, so they're all going to look pretty similar to that. Your domain is going to be all real numbers, and then your range will be y is greater than 0 because it's not going to go past that asymptote, right, of the x-axis. Alright, parent function for decay, really similar, alright? Your equation f of x equals b to the x power, but this time b is in between 0 and 1, alright? And now the general shape is going to be this. It's going to come down and then get really close to that x-axis. Again, the asymptote is the x-axis. It's going to hit 0, 1, and 1b still. And again, your range is all, your domain is all real numbers, and then your range is y is greater than or equal to 0. Okay. Flip. Alright. Here we go. Concept 1, graphing exponential growth and decay. It says tell whether each function represents exponential growth, if b is greater than 1, or decay when b is in between 0 and 1, then graph the function. Alright, so let's look at this one. Where is b? Right there. B is 2, which means it's greater than 1, which means it is a growth function. Alright, and now what I'm going to do is plug in x values, and since it is exponential, it's going to grow really fast. So I'm going to keep these values of x close to that y-axis. So I'm going to use the 5 closest, which is -2, -1, 0, 1, and 2. If I use bigger numbers, it's going to shoot off the graph. Okay, so I'm going to plug in -2 there. So I get 2 to the -2 power. Well, anytime we have a negative exponent, again, it's not a negative number. It's just a really small number. We write them as fractions. In this case, it would be 1 over 2 squared, or 1 over 4. Put -1 in there. It's 1 over 2 to the first power, or 1 over 2. Put 0 in there. Anything to the 0 power is just 1. Put 1 in there. 2 to the first power is 2. 2 to the second power is 4. Okay. Now I'm going to plot these. -2, 1 to the left, up 1/4, right about there. -2, 1/2, just up a little bit. 0, 1, right there. I have 1, 2. And then 2 to the right, 4. 1, 2, 3, 4. Okay, I'm going to plot or try to graph this. Now my line's going to look like it's kind of on there, but it's just really approaching that x-axis. And then it's going to go and shoot up. Okay, and there's the first one. Because b is greater than 1, it is growth. Alright, scoot on over here a little bit. This time, b is right here, right, which is 1/2, which is in between 0 and 1, so that tells me it's a decay function. Alright, so I know that. Now, what am I going to use? Well, just the same thing, okay? -2, -1, 0, 1, and 2. Alright, so when I put in that -2, again, it's going to be like 1 over 1/2 squared. Alright, so that's going to be 1 over 1/4. But if I do copy dot flip, it's 4. Put negative in there. -1 power in for x. 1 over 1/2, copy that flip, that's 2. Anything to 0 power is 1. Put 1 in there, I get 1/2. Put 2 in there, I get 1/4. Okay, let's go ahead and graph these parts. So I have -2, 4, so that's 2 to the left, up 1, 2, 3, 4, points I should say. -1, 2, 1 to the left, up 2, 0, 1, right there, 1, 1/2, right there, and 2, 1/4, right about there. This time it's going to swoop down and get really close to that x-axis without actually touching it, because that x-axis is the asymptote. Alright, there we go. It looks something like so. Alright, you guys. I want you to try number 2, A and B. See if you can graph these two functions. I'm going to go ahead and pause so you can take a look at the answer here. Or you pause, please. So you can finish those, and then I'm going to show the answer. Here we go. Here are the answers to number 2. Alright, I'm going to move on to the next page here. Page 3. Okay. Exponential models. Let me get a little bigger. Okay. Some real-life quantities increase or decrease by fixed percentages each year or some point or time period. Could be months or days, whatever. But the amount y in such quantity after t years can be modeled by one of these equations. Exponential growth is y equals a times the quantity 1 plus r to the t power. Exponential decay model is y equals a times the quantity of 1 minus r to the t power. What you want to take note is that a is the initial amount, r is the percent increase or decrease, the rate, percent increase or decrease, which will be written as a decimal. The quantity 1 plus r is the growth factor, right? So what's in the parentheses? And if that 1 plus r equals b, right, and b is greater than 1, that's our growth. We relate back to the graphing. And the quantity of 1 minus r is the decay factor. And if 1 minus r equals b, then b is in between 0 and 1. Okay, so let's go ahead and look at concept 2, solving a real-life problem. The value of the car y in thousands of dollars can be approximated by the model y equals 25 times the quantity of 0.85 to the t power, where t is the number of years since the car was new. Tell whether the model represents growth, exponential growth, or exponential decay. Well, I'm looking for b, right? And in this case, b is in the parentheses at 0.85. And that's in between 0 and 1, right? So that is decay. Alright. Next, identify the annual percent increase or decrease. Well, I already know since it's decay, it's decrease, right? And r is going to be representative of our percent, right? So if I go back here, I know that 1 minus r equals b, and 1 minus r equals 0.85 in this case. Subtract 1 from both sides. That gives me negative r equals negative 0.15. Divide by negative 1. R equals 0.15. Now if I'm going to make this a percent, you multiply that by 100, or you move your decimal 2 places to the right, right? So that gives you 15%, and yes, it is a decrease. I told you that because it was decay, right? And that's that. Alright. Okay. Why don't you try number 4? Take a minute to do that. Pause, because I'm going to show you the answer here. Alright, here is the answer. Also decay. And then it's an 8% decrease. Alright, number 3. Concept 3, writing an exponential model. In 2000, the world population was about 6.9 billion people. During the next 13 years, the world population increased by 1.18% each year. It is important to know that it is an increase, right? It says, for A, write an exponential growth model for the given population, y, in billions of years, t years after 2000. Okay, so increase, right, we're using this exponential growth model right here. Y equals a times the quantity 1 plus r to the power of t. Alright, so here's for a. Okay, so now what I'm going to do is just kind of plug in all this information here. So y equals 6.9 billion is our initial amount, times the quantity of 1 plus r, which is our rate, which I'm going to change this to a decimal. Okay, so I'm going to multiply it or divide it by 100, move the decimal 2 places to the left. So I get 0.0118, and then that's to the power of t. And now I'll just combine 1 and 0.0118. So now I have y equals 6.09 times the quantity of 1.0118 to the t power. And that's really the growth model that I'm looking for here. Okay. The second part says estimate the world population in 2005. Alright, so what that's telling me really is that the time has changed from 2000 to 2005, so the time is now 5. Okay, it's gone up 5 years. So now what I'm going to do is y equals 6.09 times 1.0118 to the 5th power. Okay, take that 1.0118 to the 5th power, and you get 6.06. Multiply those two together, and you get 6.49. And what we are talking about is in billions. 1 billion people. Flip it up. There is no try this on that problem, so I'm going to have to go with that. Concept number 4, rewrite an exponential function. The amount y in grams of the radioactive isotope chromium-51 remaining after t days is y equals a times 1/2 to the t over 28th power, where a is the initial amount in grams. What percent of chromium-51 decays each day? Alright, so what we're going to do with this is we're going to take our equation and we're going to plug in everything, and we're going to solve for percentage. Okay, so let's grab a... So here is our equation. Let's take this and manipulate this equation. So alright, if I take this equation, now I can kind of pull out the t. If I do this, y equals a times 1/2 to the 1/28th power, all that to the t power. So let's take this. Okay. Next, what I'm going to do is now I can do this, put this into my calculator, and I get y equals a times 0.9755 to the t power. And look, this is now our equation for growth or decay, and since what's in our quantity in our exponents is less than 1, that is decay.